how do you build a performant embedded key value store? What are the primitives that you use to build such a store, and what are the primitives that it offers? Today, I'm going to be talking about SlateDB. I manage data infrastructure at DoorDash. Previously, I built critical data systems in Microsoft Azure. SlateDB is an open source project that I contribute to. Today, this is the plan. I'm going to talk about why SlateDB matters, what is the motivation behind it, and then I'm going to describe what it is, and then we will get into the internals of how it is built. So let's start with the motivation. So you have listened to a lot of talks in the conference. There are at least 4 talks that are talking about disaggregated storage systems. Disaggregated storage system is one where the compute and storage are separated, and the compute doesn't have any state. The only state that is there is on the object store. There are a lot of examples of this. Warp Stream, for example, its brokers does not store any data. All the data is stored on S3. All the analytical table formats like Iceberg, Delta, they do the same thing. They leverage object store in a big way. Most of the data, in Delta's case, all the data is stored on object store. TurboPuffer and few others talked about this as well in different talks in this conference. Now, what do these systems have in common? What are the primitives that they use? There are 3 common techniques that they all use. The first one is immutable files. Files once written do not change. That makes caching and few other techniques, few other things easier. Batching is the second one. Batching increases latency and decreases the put cost. So that's a trade-off that you can use if you are okay with a little bit of latency. Conditional writes paired with monotonically increasing file names like 001 and so on. That's used along with write if not exists. These 3 techniques are used in a lot of the products, and SlateDB uses them as well. What I'm showing here is a tweet from Chris. Chris started SlateDB about a year back. This week happens to be 1 year since the project started. Now, what is SlateDB? I described the properties that a lot of these systems use. SlateDB is built on the principle of cloud native embedded storage, right? It is a Rust library. It offers key value interface. It offers similar interface like RocksDB, like get, put, range reads, and so on. It's implemented as a log structured merge tree. Where can you use it? It is useful for applications where 50 to 100 milliseconds latency is reasonable. Stream processing state store is one of the applications where it's directly applicable. There are few other use cases as well. There are 3 companies that have taken production dependency already. I happened to meet one of them yesterday, and I updated the slide last night. Mbucket is one of the companies. They have a booth in the ground floor. They offer Snowflake compatible lakehouse platform. They use SlateDB for metadata persistence. Responsive offers Kafka Streams as a hosted service, and they have built a storage engine called RS3 that is built on top of SlateDB. They have blogged about it as well. TensorLake, the CEO of TensorLake was in the conference yesterday, and they use it for storing documents, and they use that for serving LLMs. Now, I'm showing how you would use SlateDB. There are 3 key parts here. The crate is available, and the code, this code, as well as everything that I'm talking about is available in the URL, SlateDB demo. There are 3 important things going on here. It uses the object store crate, so it works with any kind of object store, Azure Blob Storage, S3, or anything that supports objects that object store supports. You create that, and then you create KV store. KV store in this case is the SlateDB instance. And then the first one is a put with await. That's going to wait for the file to be persisted in S3. More often, you're going to batch the writes. That is what number 2 is doing. It's writing 500 keys. And it sets await durable as false. What that is going to do is the statement in number 2 is going to exit immediately, and the flush statement in number 3, that is the one that's going to persist the data. We are going to get into the internals, and I'm going to describe what happens behind the scenes when this code is executed. Now, with that, here is the plan for internals. I will start with writes. Writes is going to create smaller files, and compaction is the one that's going to make the files better. After that, I will describe reads. And manifest is the one that ties all of these things together. Manifest describes the state of the database. And after that, we are going to look at few interesting aspects of SlateDB, checkpoints, writable clones, and how they are implemented. This is a very busy picture. It has a lot of parts. I'm going to break this into small pieces and describe it as we go along. What it shows is the state of the database. It has 2 sections, right? Stay with me. I'm going to break this into smaller parts. Let's start with writes. Write has 2 steps. The first step, you see in the memory, it has 3 keys that's batched, and when a flush call is made, an SST file is created. There is also a setting called as flush ms milliseconds. So every flush ms milliseconds, an SST file is going to be created as well. It is created in a folder called WAL, write ahead log. An SST file is a sequence of data blocks, and each data block is a sequence of key value pairs, and then it has metadata footer. The footer has the first key for every data block and Bloom filter and few other aspects. So that is what is there in the SST file, and this is step 1. There are 2 terminologies here, SST file, and then an SST file in the WAL folder is, again, it's called a write ahead log in the SlateDB terminology. Now, step 2 of write, there is a second setting called as L0 SST bytes. This is usually in the order of like 50 to 100 megabytes. When a lot of write has happened, file is created in the compacted folder. In here, we are looking at xyz.sst, and that is a SST file, has the same structure as the WAL file. When that file is created, it is not part of the database yet. A new manifest file is created, and in the manifest file, you see 2 properties. The first one is L0. It's an array of files. The XYZ is added to that, and then WAL ID last compacted, it's set to 3. As I shared earlier, it is using one of the techniques, which is numbered files and conditional writes. So the number 3, what it means here is write ahead log number 1 and number 2 are not part of the database anymore, and the content that is there is now in xyz.sst. So that is step 2 of writes. I'm showing the same thing here in a sequential order. In the first one, it creates a SST file 001.sst. Second one, nothing changes on the object store, and in the last step, you see that both an SST file and a manifest file is created. So we are looking at the picture again, and we are looking at the right portion of the picture alone, and it has 3 kinds of files: manifest, write ahead log, and compacted. Now, both the writes, the flush ms milliseconds writes, and the L0 SST size threshold based writes, they're going to create smaller files. There is a different component called compactor that takes these small files and then creates larger files. And these small files have overlapping keys. When compaction kicks in, it's going to create sorted runs, and they don't have overlap. They have non-overlapping keys. Every time a compaction runs, it creates a new manifest file. So step one of compaction is take the small files, create a bigger SST file. Step two is create a new manifest that has the updated state of the database. So what we are looking at here, first step, there were two SSTs, compacted is empty. After compaction, both of that, the data from both the files is in the compacted SST, and then L0 loss compacted is updated to B2. Example number 2 is, example number 3 is slightly different. It takes 2 sorted runs and then creates a different sorted run. So that's what compaction does. So what we have covered so far is there is an SST file, there is a sorted run, and there is a manifest file. And manifest file describes the state of the database, which is the list of SST files that are part of the database at any point in time. So we are looking at the same picture again. In object store, you see there are 3 kinds of files: write-ahead logs, compacted. Compacted is created by the compactor component, and then manifest file. Manifest files are updated every time there is a change to the database. Now, let's get to initialization. Assume that a lot of these writes have happened, and on the left side, what we are seeing the state of the object store. There are 3 folders, and then first step is it finds out the recent manifest. It lists the manifest folder and it finds the recent manifest. In this case, it is 004.manifest. And it loads that manifest into memory. And that manifest has few things. It has the L0 files, ABC, and then it has the compacted. It's going to store the metadata about that in memory. The metadata is what is the first key and what is the Bloom filter. It's going to store that in memory. And then it's going to list the val folder. It's going to find 3 files, 4, 5, and 6.sst. We see here val ID last compacted is 4, so that is not part of the database. So it's going to only load 5 and 6. And the key value from that is going to be stored in memory. So that is initialization. After it has done that, it's also going to create a new empty write-ahead log, and then it's going to create a new manifest with the incremented writer epoch. This is necessary because we want a single process to write. We don't want 2 processes to write to the database. And the process that I described here in terms of creating an empty write-ahead log, incrementing the writer epoch, and creating a new manifest, that is the one that ensures that there is a single writer. This is the formal validation of this is done by a tool called FISB. It provides very lightweight formal validation. So that's initialization. So far we have looked at writes, and then we looked at compaction. And now initialization is going to bring all of that back, right? Reads. SlateDB is implemented as a log structured merge tree. Reads are like any log structured merge tree. So it's going to go level by level. And I shared that it has few things in memory. It has the first key for every SSD file. It has the Bloom filter, all of that in memory. So the way that read is going to work is it's going to go level by level. There are 2 kinds of reads that are supported. One is uncommitted read, and second is committed read. Uncommitted read serves data that is in memory as well. Committed read only serves data that is persisted to object store. Now, I am describing what happens for different kind of keys. This is like any log structured merge tree. Get 1 uncommitted, the data is in memory, so it returns that. And something like get 6, it's going to look at it in every level, and then it's going to return it from the compacted folder xyz2.sst, and get 10, it is not there in any of the files, so it's going to return none. There is a lot of caching going on. In memory, it stores the key ranges and the Bloom filter, so that's going to be used to ignore a lot of these files. Files are split into, the SST files are split into parts, and those parts are cached locally as well. And when available, that is used too. So that reduces the amount of data that it reads from S3. Early on, I shared that files are immutable. All files that are created by SlateDB are immutable, and that's what makes caching easier. That's what makes caching simpler to implement. There are bugs in this slide. If you notice, you can comment in the uploaded video or let me know later. Those are intentional. Okay. Now, yeah. Sure. So now manifest. I have been talking about manifest. Manifest is the one that has the state of the database. There are a few interesting properties here. First one is the manifest ID. That is going to be the same as the file name. And we talked about vol ID last compacted. That keeps track of which of the write-ahead logs are now part of L0 and so on, right? So that's what a manifest is. Now, when is a manifest created? Whenever there is a state change, a manifest is created. Now, a new writer is a state change. Compaction is a state change. And those are the places when a manifest is created. I described that a lot of these small files are created, and every state change creates a new manifest. So a lot of files are going to be not required anymore. That is where garbage collection comes in. It gets the current manifest, it finds all files referenced by that manifest, and it deletes everything. So we don't have to pay for storage for these files that are not necessary. And compaction is taking small files and then creating larger files. These are maintenance operations. The interesting thing about SlateDB, because the state is all in object store, it's possible to run these things in a separate process. And what that allows you to do is the serving layer is not overloaded with these maintenance operations. They are implemented as two different components, and those components can run either on the same machine or they can run on different machine. And there is nothing more that we had to do to implement something like that. Now we are getting to a few interesting features of SlateDB. The first one is checkpoints. I talked about garbage collection, deleting the files that are not necessary anymore, but sometimes you want to look at the old state of the database. An example, let's say you have a Kafka streams and you are using SlateDB as the state store, and there are two consumers. One of them is looking the data as of now, and the other one is looking data as of like few minutes back. The one that is looking the data a few minutes back, it can read an older manifest and it can read the state of the database as of that timestamp. Now, to implement that, two things had to happen. The old manifest should still exist, and all the files that are referenced by the old manifest should still exist. The garbage collection shouldn't delete it. Only thing that had to change for that is there is a new property in the manifest called checkpoints. It's an array of manifest IDs that we should not delete. With just that, we are able to implement time travel reads, and it's useful for a couple of cases. One is read-only clients that want a consistent snapshot. They can just open an older manifest and then they get the state of the database as of that manifest, right? Read-only clients can also tail the manifest creation. So you can have a single writer and multiple readers. The readers can be on any number of machines. So you can have read throughput. Can have a very high read throughput with that approach. So that's checkpoints, and that is time travel reads. Next thing is writable clones. The scenario is something like this. Say you have a Flink application or a Kafka Streams application, and it is using SlateDB for state store, and you want to experiment with the change. You want to write the new version of this application. You would want to start from the state, and the new application is going to mutate the state as well. You don't want the production version to be impacted with this change. To do this, usually you will have to copy the data completely, but if you can create cheap clones, that is better. That's what writable clones does. You create a clone, and then the clone and the parent database evolve independently. There is only one new property to implement this, parent DB. It is a reference to the parent database, and all it is the path and then the checkpoint of the parent, checkpoint in the parent. With that, you get a writable clone. Only metadata is copied. All the SSD files are referenced, right? So writable clones is another interesting feature, and writable clones is used in, I think Responsive uses it for implementing some of their use cases. Okay. With that, we have come to an end to the internals of SlateDB. This slide shows the features that I talked about. These are very good primitives on top of which interesting applications can be built. Something like remote maintenance operation, writable clones, these are all things that we are able to do because of an object store first design. All the things that I talked about today and few more are available in this RFC, in this folder, and the pull requests behind them have a lot more interesting discussions. I did not discuss few of the features that are here, range queries and merge operator. They are very interesting features. Timestamps is another important one. If you are interested, you can look at this folder to look at the design behind these features. What we have built so far is just the beginning. There are a lot of interesting things that are still happening on SlateDB. I am listing 3 important things that are on the roadmap. First is language binding. I shared that this is written in Rust. It's an embedded Rust library. Language bindings will enable us to use this in other languages. Change data capture so that you can take the state of SlateDB and replicate it to another system, something like Iceberg, and transactions so that stronger application semantics can be implemented. Getting started. SlateDB.io, that's the website, and all the code that I talked about today, the features, that's all in SlateDB demo, the second link here. And if you want to contribute, there are a lot of good first issues. Now, to summarize, building a performant key value store on object store is very much possible, and it only takes a handful of techniques. And tools like SlateDB unlocks new possibilities, and they enable new applications to be built. Thank you.